watch NCIS or you watch, what's the other one? CSI. They're always using instrumentation to get stuff to come out with the material. And one of the things that they use is a GCMS. They're always going to go into the GCMS, and they're trying in the GCMS to figure out whether or not it's chemical A or chemical B or this poison or that poison or whatever. And the GC stands for gas chromatograph. And most of you have dealt with chromatography at some point or another. And the most of you have dealt with, you get a piece of filter paper, coffee filter, the cheapest marker you can find, right? Sharpie's no good. Crayola markers, no good. Dollar General markers, best. Okay, whatever cheap, crappy marker. And you know, if you did this with a bunch of kindergartners, you made little dots like this, and then you stuck it in water, and the water would creep up, and it would create these smears up here. And the most common are coffee filter butterflies, right? You've all have seen the coffee filter butterflies. And what it is, this happens to be what they call liquid chromatography. And depending on what color and what chemical you have, depends on its transport time using water, or you could use alcohol, or you can use a variety of different things. What that transport time is to have it stretch up, and it will separate the colors. That's why I say Sharpies are crap. Crayola markers are crap, because they have really, really good stabilizers that are going to keep the mixture together. The Dollar General ones don't have good stabilizers in it, and so it's allowed to spread a lot better. So if you're ever making coffee filter butterflies, use the cheapest markers you can find, because that's what's going to happen. So that's liquid chromatography. In gas chromatography, you've got a column that's packed with, and it could be packed with glass beads, it could be beads that have different types of materials on them, and you're doing essentially the same thing, except now you're putting a carrier gas, and that carrier gas can be nitrogen or helium, and you insert a really tiny amount of a liquid sample into the chromatograph. Between temperature and the flow rate of the gas, you're going to get separation of the materials. So different chemicals will come out at different molecules will come out at different times. Now what happens is, I can, depending on what I'm doing, I can use just that time residence to do that separation, but a lot of times you go into a different device, hence the MS portion. So once I get that separation, I go into the MS, and the MS is called a mass spectrometer. And this is why I'm a chemical physicist and not a physical chemist, is because I wanted to understand how these instruments worked. And so a lot of my analytical techniques and stuff when I ran a quality control lab, it's because I understood the inner workings of these different instruments. So the mass spectrometer, and what the mass spectrometer does is, now from the gas chromatograph, we've got a little molecule that goes through, right? And we've got a coil here. Oh, I forgot to bring my Lenses Law tube. Apologize, I forgot to bring it. But I've got my tube, and we've created an electric field inside this tube. All right, so my little molecule is going to enter in here, and it's going to go through an electric field, and you can control, because we know we can do that, because we've been talking about it when I do a capacitor, we can control the magnitude of the electric field, so we can put it in, and I'm actually going to give it a value of 950 voltmeters. Now, it's going to come out, and this is depending on the type of instrument you have. You can have a single pole or a quadrupole mass spectrometer, and that's going to talk about how fine a separation that you can get, but we're just going to do it as a single pole here. And so I'm going to go in here, and I'm going to have a magnetic field. And again, we know, because we can build it, we can set the magnetic field. So I'm going to start with a magnetic field, and for mass spec instruments, the magnetic fields aren't all that strong. They don't have to be, okay? They don't have to be to do what we need to do. So when my little molecule, or in this case, a charged particle, so we're going to do it as a charged particle, I get a charged particle out here, and it hits my magnetic field. And one of the things that we know happens is I'm going to have that force on the magnetic field, and my particle is going to travel in an arc. And over here, it's going to hit some sort of detector. And depending on your instrument, it can be a photoionization detector, it could be a flame ionization detector. It's going to hit some sort of detector that says, bingo, I've had a collision with a particle against the wall. And this part becomes the important part, because it comes in, and what we end up doing is we look at the radius of this circle that comes in and hits that detector, and we can figure out what the material is, because we're about to show you how that works. So what we're going to do is we're going to take a charged particle that has a mass of 2.18 times 10 to the minus 26 kilograms. It's going to have, we've charged it, and so it's just going to have one charge. So I've just got a charged, a +1 charge. So I could have a helium, or I could have a hydrogen cation. I could, some sort of cation, could be a lithium cation, could be a potassium cation. And the key is we know the mass, and we know that, and because if I'm building a mass spectrometer, I need to know where to set my detector, is what I end up having to do. So we can actually do that. So the question is, what's R? Now usually what's happening to us is we want to know what M is. That's usually what we're doing, because that's usually going to tell us what the substance is, if I know what M is. So, but usually what I'm looking for is M, but this time we're going to look for R. So if I do that, what we want to look at is that we've got the max force associated with the magnetic field. We can assume that because we've actually set it up that way. We've set it up that it's perpendicular, and that's going to equal, that force, that's our max force due to the magnetic field, is going to equal the centripetal force. I can't spell today. Centripetal force. And if I do that, this is Q velocity magnetic field is equal to M velocity squared R, because that's my centripetal acceleration from way back when. And that's my magnetic field. So I'm going to solve for R. So R is going to equal mv squared qvb. One of my velocities cancel out, so I get mv qb. I know that I don't know velocity. That's okay. Okay, that's okay. Because I can go back and remember, because we've been looking at it, that force is equal to charge times the electric field, which is equal to charge times velocity and magnetic field. Charges cancel. The electric field divided by the magnetic field is going to give me velocity, which is really cool, because now I don't, the only thing that's going to change in my instrument is dependent on the mass. I just got to make sure I have a charged ion, because I don't even know charge for this, for velocity. I don't even need to know the charge. So now I can go plug that back into here. So now I get M E over B Q B, and that's going to give me M E Q B squared. And that's going to be my radius. That's where it's going to hit the detector. So now I can just plug in the numbers. So my mass was 2.18 times 10 to the minus 26. my volt, and that's in kilograms. This is 950 volts per meter. This is 1.602 times 10 to the minus 19 coulombs, and I get 0.93 squared, and that's Tesla squared. And when I do that, I end up with 1.5 times 10 to the minus 4 meters, or it ends up being 0.15 millimeters. So it's a really cool way to get separations and be able to tell where what we're doing. So if I'm looking at, so if I want to rearrange this equation, because usually it's not the radius. When I'm building a mass spec, I have to worry about the radius. But when I'm actually using the mass spec, I end up with, so I've got MEQB squared is equal to R. I'm going to end up with mass is equal to R QB squared divided by the electric field. And this is actually what I measure in the instrument, so I can come back and figure out what my mass is. So it's really, and so they use software to help figure that out, but it's a really cool instrument to work with where we're dealing with the electric field. Now, let's go back and look at this. Velocity is electric field divided by magnetic field. What we've been working on, okay, what we've been working on is if I have a wire and I've got current in the wire, we get a magnetic field. And if I put my thumb down, curl my fingers, it's coming out of the page over here, it's going into the page over here. We get a magnetic field, right? That's one of the things we've shown. The other thing that we've shown is if I have a loop of wire and I take my bar magnet, doesn't matter whether it's north or south, and I'm moving this bar magnet, I'm going to generate a current. So the observation that we have is that current generates a magnetic field. And that a magnetic field generates current. And if I've got current, remember current comes from the electric field. It's just that it's easier for us to measure current than it is for us to measure the electric field. So if we go back, when we derived current from the electric field, we actually talked about it in the wire, right? We talked about it in the wire, and that's what's creating my little electrons. They're cascading through. I've got lots of little collisions, but it looks like I get a flow of electrons through my wire. But that's what's happening. I get an electric current generates a magnetic field. Magnetic field generates current. These two things are related, and that's going to become very important probably next week. Okay, it's very important really quickly. So we want to kind of keep that in mind where we're at. So the other thing that we've been doing is we've talked about flux, and we've got magnetic flux, and remember we've had electric flux as well. So that's my maximum, this is maximum, is when my magnetic field is perpendicular to the area, I'm going to get maximum flux. And if I'm at something else, it's going to look like this. And if we think about it, if here's my magnetic field, and I have my loop here perpendicular, that's when I'm going to get my max flux. If here's my magnetic field, and my loop is like this, I get flux is equal to 0. And then if we have our magnetic field, and my loop is something like that, I got to worry about my angle for my flux. And we saw the same thing in the electric field. So there was a flux in the magnetic field, there's a flux in the electric field. There's lots and lots of parallels between magnetic field and electric field. Even though experimentally, historically, people understood magnetic fields a little bit better than they did electric fields, it's easier to measure and play with electric fields before we get to the magnetic fields, which is why we go backwards and teach electric fields first. So it's an artifact of history how we do it. So one of the things that we showed, was it Friday or Wednesday? I don't remember which day it was last week. I'm confused. I'm confused as to when we did it. But we showed the Faraday's law. We showed Faraday's magnet, right? And we did the levitate. I showed the video with the levitating barbecue, which is a really cool video. I love that one. And then we did the wires, and we showed that if I had one loop of wire and I had my little deflection, you know, we could look at this little instrument and we could see the little needle move. And if I had more wires, I had a nice coil of wire, the deflection got bigger. So let's kind of remind ourselves of some terminology. So in this chapter, we go back to using EMF instead of voltage. And EMF is that lovely force, or that presumed force, that is the maximum possible voltage the battery can provide between its terminals. So that's going back to when we actually defined voltage, and remember that we could find that internal voltage that came up, and this was the voltage that you could think of if the battery is a charge pump around a circuit. So just kind of remembering that's the case. Well, Faraday was a great experimentalist. He was a crappy mathematician. So he relied on others to actually kind of give us back our equations. He did a lot of the demonstrations of it, and we could actually write Faraday's law of induction this way. That voltage that we saw was the result of a change in flux with respect to a change in time. Now this negative is an interesting thing, and that's why I'm kind of bummed I didn't bring the Lenz's law tube with me today, and I'll have to take a video of it and post it. But the Lenz's law tube, basically what happens is you take a tube that is a conducting material, okay? And if I drop a marble through that tube, it's going to fall just like it would fall right there, right? I mean, we know and we can experience it and we can see it, it's going to fall. And they're going to hit, if I drop the little marble through the tube or I drop it over here, it's going to hit the ground at the same time. Now, if I drop a magnet through here, we'll sit and wait and wait and wait and wait and wait, and ultimately it's going to fall through the tube. We got a problem. Now, if I drop the magnet outside the tube, it hits the ground just like the marble does. But if I drop it through the conducting tube, something happens. Well, think about this. It's got a little magnetic field floating around it, right? So what happens is I'm going to generate a current in the tube. Well, the current's going to generate a magnetic field, right? Well, now I have a little bit of a magnetic field that's opposing the motion of my magnet. So it's going to act like a lag. Now, because my magnet has weight, right? It has weight. It's going to fall with relation to that weight. And remember that my motion is going to be the sum of the forces is going to be the force due to gravity minus my opposing force due to the magnetic field. So it's going to ultimately slow it down. It's going to take longer for my magnet to fall through, because as I fall through, I'm generating a magnetic field that's opposing the motion of the magnetic field of the magnet that's falling through the tube. And that's why we call it Lenz's law tube, because it demonstrates Lenz's law. And Lenz's law says this, and this is where this negative sign is going to come from. And I'm going to write it out. The induced current in a loop, and you can think of your conducting tube as a series of infinitely small loops, right? Because that's what it is in the direction that creates a magnetic field that opposes the change in the magnetic field flux, the magnetic field flux through the area enclosed by the loop. So the induced current in a loop is in the direction that creates the opposing magnetic field that's created by the changing magnetic field flux. It's a little hard to get your head around it. We're actually going to work a problem that hopefully will help get your head around it. That's going to be one of the difficulties about the homework that you're about to do. Is there's going to say, okay, we've got a wire and I've got a loop. What's the direction of the current in the loop? Much easier to measure it, which is one of the reasons why Faraday was kind of a bad mathematician, because he liked to measure everything. He was very much empirical. So it's one of those pieces that's there. But this demonstrates, as my little magnet is falling through the tube, why it's going to take it along, because if I get this opposing magnetic field. This also explains why I can't generate so that I'm building my magnetic field and ultimately have a perpetual motion machine. Because I've got to have that opposing current. So let's kind of work a problem to see if this helps out a little bit. So I'm going to take a square loop of wire. Actually, it's going to be multiple. So it's going to be a square loop. Each side is 0.5 centimeters. There are going to be 25 loops of that wire. 25 loops of that wire. The resistance of our whole coil is going to be 0.4 ohms. We're going to apply a magnetic field perpendicular to our loop so that we're going to have the maximum deflection, or the maximum that we can have. So our magnetic field is going to be applied perpendicular, and we're going to move it uniformly. So think about a bar magnet moving through our wire, and we're going to change from 0 Tesla to 0.25 Tesla in 0.3 seconds. Now remember, if my magnetic field is stationary, I'm not going to get that induced current. Remember watching the videos. If I'm just sitting there holding my magnet inside the loop, nothing's going to happen. It's when I'm moving that magnetic field that something's going to happen. So we want to calculate the induced current or well, we're going to calculate the induced current or the induced EMF. We're going to start with EMF. And we want to find the magnitude and direction of the current. So we're going to end up getting the current, we're going to get the EMF, and we're going to find the direction of the current. All right, so the first thing I got to do, so I did give you Faraday's law. Faraday's law was this right here. But I didn't give it for a loop or a series of loops or series of coils. So I can put in N, which is the number of coils. And remember that flux is going to equal the magnetic field perpendicular times the area. So I'm going to end up getting my induced EMF is going to equal the change in my flux with respect to time times that, which means I'm going to need N, and I'm going to do this B final minus B initial times the area with respect to my change in time. Now, I'm given this, I know that, so I need to calculate area. So we can calculate area. That's easy enough, because it's going to be length times width, which is going to be 0.5 times 0.5, and this is going to be centimeters squared, which is going to give me 0.25 centimeters squared, which is equal to 0.0025 meters squared, because I need to be in meters. Now I can calculate my flux, okay? I can calculate the change in flux, or I can calculate the flux. So I'm going to do the flux max is going to be my 0.25 Tesla times my 0.0025 meters squared. That's going to give me 0.000625 Tesla meters squared. And a Tesla meter squared is another lovely unit called a Weber. So I end up with 0.000625 Webers. So that gives me my flux. So now I can calculate my EMF. My EMF is going to equal negative, I've got 25 turns in my coil. I'm going to have my final flux is 0.000625 Webers. My initial flux is 0. And my change is 0.3 seconds. And when I do that, I end up with a negative 0.052 volts. But current is just my change in voltage divided by resistance. So if I'm finding magnitude, I don't have to worry about direction. So I get 0.0052, or I put too many zeros, 0.052 divided by the resistance, which was 0.4, and that's volts per ohm. And we've done this enough time to give us that it's 0.13 amps. Okay, now we've got to figure out direction. And this is where Lenz's law comes into play. So, here's my square. Here's my square coil. we're going to start with the magnetic field this way. So that's the applied magnetic field. So if I do this, my magnetic field, and I am doing this, and I get my magnetic field, and remember, if I lay my finger, my right hand rule, if I lay my thumb along the direction, I'm going to get the magnetic field. So this is what would be if I had a current in the wire getting my magnetic field in this direction. All right, Lenz's law says that I have to have an opposing current because I have to have an opposing magnetic field. So if I'm going to oppose it, I have to flip it over. So if I'm flipping it over, my current's going to go this way as viewed from the top. And if I go ahead and take this around, there it is as viewed from the top. My current is going to be clockwise as viewed from the top. Okay? So you see how I did it? If I'm going to a magnetic field this way, this is how I'd have to do my right-hand rule to get that magnetic field. But Lenz's law says that the induced current is going to be in opposition to that, so I have to flip it over, which has me doing the current in the wire this way. That's the induced current in the wire. And that means I'm going this way as I'm going around. I'm going to be clockwise as viewed from the top. You just kind of got to play with it. You just kind of got to play with it. So hopefully that kind of gets you a little bit better as to where things are. So on Friday, we discussed generators and motors. There's a generator and motor homework that's out there specifically to that. There will not be a generator and motor problem on any test. I won't do that to you.
I thought the generator and motor wasn't due until next week.
It may not be.
Okay.
But there's a homework out there.
Okay, yeah, there is.
There's a homework on generators and motors.
Just because I was on there yesterday, I was like, you didn't change the due date, did you?
No, I didn't change the due dates. Because I think what I have for you guys for homework, I think everything is out there and available except for the quizzes. And that way you guys can be working ahead if you want to.
Yeah, we have 3 assignments due.
Yeah, because all the magnetism stuff, I grouped it all together because I didn't know how I was going to get through all of that stuff. But I think I haven't, and I'm not anticipating changing dates. But I know I got to get a magnetism quiz out there for you guys so you have an extra quiz in there. And for magnetism, it's probably going to be a take-home test. So just from a timing point of view. Because the final will only be optics. So we've talked about motors and generators. We did this problem on Friday, all right? No, it is not figure 3111 in your book. It's in my other book, it's figure 3111. It's a classic physics problem that we end up doing. Because we end up doing the sliding bar along the magnetic field, which ends up working, we've done this problem a couple of times. It's an example in the book that you end up with. You get a balance. And this actually helps us do devices like electric guitars, that kind of stuff, right? Gives you the weird sounds and all that fun thing. So we've done that sliding bar problem. And we did motors and generators on Friday. But now, that's actually, so getting us back on track in our chapter, we are actually getting ready to define inductance. So if I go back and look at this, I end up with my good old Faraday's law problem here. I get my flux divided by, this is my change in flux divided by my change in time. I can actually look at this in terms of a device, okay? And I can, because we don't deal with changing flux, right? That's not something that we do. What we end up doing is we change current. And my change in current is what's going to cause that deflection. You know, we get that change in current. That's what we can actually measure. That's what we can actually see. And so I want to go from here, and I can actually do that if I create this thing right here. And that's a proportionality constant. And you can play with the mathematics if you want to. But what this is actually saying is it's saying that the self-induced EMF must be proportional to the rate of change of the current with time. So if you want to go play with it, you can get to the proof there. But we want to worry more about this little gizmo right here. We want to worry about that. So we're going to call L, and L is essentially a proportionality constant. I couldn't spell today because I put the O and the R in the wrong spots. It's a proportionality constant called inductance. Okay? So think of L. So L is this lovely thing. We've defined an R, and we've defined a C. So I can have resistors, I can have capacitors, and now I've got inductors. So it's actually a little device that I can put into a circuit. I can actually put into a circuit. Now L has lovely units. L is 1H, which is 1 volt second amp, and this lovely thing is a Henry. So that's a Henry. And so inductors are in Henrys, just like capacitors are in Faradays, and resistors are in ohms. So inductors are in Henrys. I can make an inductor, and my inductor ends up being a little solenoid, a little coil of wire, and I can actually do this coil of wire. It's N I, the flux, divided by current, and I can actually calculate inductance. This is permittivity of free space, the number of turns, the area that is enclosed per unit length. So we can build these devices. We can build those devices. So I can take a solenoid and your slinky, your magnet, you know, if I put a current in my slinky, I can create a magnetic field. I can actually have a slinky as my solenoid. So what we're going to do is we're going to calculate the inductance and self-induced EMF of a solenoid, our little curly Q thing, that has 300 turns, has a length of 0.25 meters, and the area, our cross-sectional area, is going to be 4.00 times 10 to the minus 4 meters squared. So we're going to build a little device. So we're going to use that the inductance is going to be the permittivity of free space, the number of turns squared times the area divided by the length. And that's going to give me 4 pi times 10 to the minus 7 Tesla meters amps, 300 turns. And then I get my 4 times 10 to the minus 4 meters squared divided by my 0.25 meters. And when I plug that into the calculator, I get 1.81 times 10 to the minus 4 cool units, Tesla meters squared amps. But that ultimately is a Henry. ultimately ends up being a Henry. And so I can actually write this as 0.181 millihenries. So once I've got that, my induced EMF is minus L, change in current with respect to time. And if I decide to put this is where we're going to say it. So if I've got a decreasing current at 50 amps per second. So our current in our system is decreasing at 50 amps per second. I'm going to take my 1.81 times 10 to the minus 4, and there's my negative, henries, minus, because this is a decreasing current, 50 amp seconds. I get an induced EMF of 9.05, it works out millivolts. Kind of keeping it so we're not carrying a whole bunch of times 10 to the negative numbers. So if I have a decreasing one, I'm going to plug in the negative, and I'll get an induced EMF of 0.905. So what this means is this. So we go back, and we've had, this is my good old circuit. Let's kind of talk about this for a second. This has got a resistor in it. When I go and look at my current or circuit with a resistor, I've closed the switch, I get an instantaneous response associated with the resistor. We've also looked at a system where if I have a capacitor in there, I don't have an instantaneous response. It's going to take a little time for that capacitor to charge up before I get current through the circuit. Well, what happens in a system like this, and how we actually draw inductors in our circuits, we do the little curly Q thing. So this is L, so this is C. I've got something that's happening in my circuit, so as soon as I flip the switch, we can look at L as the measure of the opposition to the rate of change of current. So what's happening is when I close the switch, my inductor essentially doesn't want the current in the circuit to change. It's not happy when the current is changing. So my inductor is the measure of that opposition of I don't want the current to change. So if I start out with current in my system and I open the switch, the inductor is going to try and keep the current going. Or the inductor is going to try and prevent it from not happening. So we get an opposition to the system. So we can look at that piece, which means that this has a time factor associated with it. And in RC circuits, so when I had a circuit like this is what we saw. If I put in a resistor here, and I have a capacitor, we had the time constant was R times C. And that was how long it took for the capacitor to charge up and how long it took for it to delay off. I'm going to get for what we call an RL circuit. So it's going to be pretty much like what we had before. I'm going to have a resistor in here. And I'm going to have my inductor in here. And so that's an RL circuit. I'm going to see the current come in, go just like that. And current is going to end up being E over R 1 minus E to the minus T over my time factor, just like I saw in the RC circuit, except now tau ends up being L divided by R. Okay? So my time factor for this is going to end up being that piece right there. And it's going to work very similar to what we saw in RC circuits. One more thing, we got to do one more thing, and this will actually cover everything that's in this chapter, is those things will store potential energy. My inductor will store potential energy, and that's stored and essentially with the magnetic field in my system, and that's going to be 1/2 Li squared. And if you remember, for my capacitors, the potential energy in a capacitor is 1/2 C change in voltage squared. So we see some similarities between how these components are going to handle. And it's going to become really, really important when we get to alternating current. Okay? Because in DC current, once I close this switch, and once my inductor is done getting rid of the change, nothing's going to happen, right? I'm not going to get a change in current. But let's go back here and let's look at the EMF. EMF is equal to minus L, change in current with respect to time. In an AC circuit, what's happening? My current is always moving. So when I'm building circuits with DC, it's no big deal, because if I put an inductor in there, all that's going to do is give me some time when my switch is opening and closing. But my inductor becomes really, really important when I'm in AC current or alternating current, because my current is always changing. And if my current is always changing, guess what's happening in my magnetic field? My magnetic field is always changing. And so my inductors become really, really important in AC circuits. Really important in AC circuits. So we're going to work a problem here. So we've got a battery. It's connected in series with a 0.32 ohm resistor and an inductor. The switch is closed at t is equal to 0. The time constant is 0.12 seconds, and the maximum current is 8.1 amps. We want to find the EMF of the battery, the inductance, the current after one time constant, voltage across the resistor, and the voltage across the inductor. So we're going to find lots of information from that brief problem statement. Okay. Rule number one, and I've probably said it, if you guys had a nickel for every time I've said it, you guys would probably be able to pay for your books, right? Don't make it harder than it is. Don't make this harder than it is. All right, EMF of the battery. V is equal to IR, or I max times resistance is going to equal my EMF. EMF is going to equal so I got my I max right there, times resistance. My I max was 8.1 amps. My resistance in the system was 0.32 ohms, and it's 2.59 volts. Because I'm sure a lot of you said, I don't know how to do this. Yeah, you do. You've been doing it a lot. Okay. Same rule. Inductance. Don't make it harder than it is. We're given the time constant. Time constant is 0.12 seconds. Time constant is L over R. We know what R is, so I get 0.12 times my resistance, which is 0.32 ohms. That's going to give me L, which is going to be 3.84 times 10 to the minus 2 henries. Okay. When it says calculate the current after one time constant, that means T is equal to tau. That's what that's telling you. T is equal to tau. Current is equal to I max 1 minus e to the minus t divided by tau, which becomes I max 1 minus e to the minus 1. And if you remember it and remember it from the graphs and stuff, that's 0.632 I max, which is 0.632 times 8.1, which is going to give me 5.12 amps. Then it asked for the voltage across the resistor at one time constant. So we know that T is equal to tau. We know that I is now 5.12 amps. V is equal to minus IR. That's going to be my 5.12 amps. And it's a voltage drop across the resistor, which is why it's negative. 0.32 is my resistor, and that gives me a negative 1.62 volts. Now the last part's a little harder. The last one in our problem, the voltage across the inductor, is a little harder. So let's draw our circuit. So I'm putting my switch in. I'm putting an inductor in. And I'm putting in my resistor. So I have a circuit. The thing here is that Kirchhoff's rules apply. So my Kirchhoff's rules apply. So if I do this, I'm going to get the EMF of the battery plus the change associated with the change in voltage associated with the resistor, and plus the change in voltage associated with the inductor has to equal 0. So I get my EMF minus my resistor minus the change in voltage associated with the inductor is equal to 0. Or plus, we'll just leave it as plus. So I get the change in voltage is going to equal IR minus my EMF. My IR is from the previous one is 1.62. My EMF that we calculated was 2.59. This gives me a negative 0.924 volts. Yeah, so this is the tricky part of the problem, primarily because it may not be obvious that Kirchhoff's rules still apply. That loop rule still applies. So I can go in and plot in the numbers. And now we're finished with this chapter, and we get to start alternating currents on Wednesday, or Friday. Don't everybody get all excited. Don't everybody get all excited. Yeah. Yeah. So. You guys good over there?